Welcome to Study Loop.
We're given a data table and told that our company develops radioactive isotopes for medical applications. We measure the activity of a radioactive sample, and we want to find the half-life of this sample. So first, noting that the activity, dN/dt, is equal to lambda for the K constant times n, the number of samples that we have at some given time, we can write this in the exponential decay form, lambda times n naught, the initial number of atoms that we have in our sample, times e to the minus lambda t. Solving for the natural log of dN/dt, the activity, we find that we have the natural log of lambda m naught, and keep in mind that this is just some constant value, minus lambda t. So now if we were to plot the natural log of dN/dt versus t, we would find that the slope has a value of minus lambda, because this is like a slope of mx plus b, or in our case b, the constant, is given by this natural log of lambda m naught, and m, our slope, is minus lambda. So plotting the data table, we get something that looks roughly like this. And if you're careful with the numbers, you'll find that this slope here, which is, we said, is equivalent to lambda, has a value of 0.5995 inverse hours. So now we can use the fact that lambda is equal to the natural log of 2 over the half-life to solve for the half-life, which of course is just the natural log of 2 now over lambda. And this works out to be 1.16 hours. So the next thing we want to find is how many radioactive nuclei were present in the sample at time t equals 0. So at time t equals 0, let's get a new page going. At t equals 0, the activity, dN/dt, is simply equal to lambda times n naught, the initial amount of sample that we have at time t equals 0. So now, if we solve for n naught, keep in mind that this has to be a positive number, so just to be safe, we're going to take the absolute value of dN/dt. This times 1 over lambda will give us our initial sample. And keeping in mind our units, once again, we'll find a value of 1.201 times 10 to the 8th. So this is the number of radioactive nuclei that were present at time t equals 0. So now for part C, we want to find, after 7 hours, how many nuclei are still present. So this simply follows from, again, using the exponential decay formula, n naught times e to the minus lambda t, where all these are known quantities, and we simply plug in 7 hours for the time, and we'll find that n is equal to, after keeping our units straight, 1.807 times 10 to the, and that's how many nuclei are present after 7 hours.